Woohoo, we are live. This is Math 40, and this is 3.4, and we're going to be learning about slope and rate of change. Woohoo, yay! So, to begin with, we're going to pretend that we're going to go skiing down a mountain. Now, if you've never gone skiing down a mountain, just imagine that you're going skiing down a mountain, or roller skating or skateboarding. And we want to draw examples of the following. So, the first thing we want to do is draw a very steep slope. So I'm going to draw a mountain that has a very steep slope. To be honest, I don't think you could actually ski down this. Yes, that's exactly, I guess we're snowboarding, huh? This is really more snowboarding. I don't think we could actually go snowboarding down this, but maybe some people do. Okay, what about a slightly steep slope? Now, I'm going to say if this is really steep, I'm going to say, this is kind of like a bunny hill situation. This is the kind of slope I've been on. You don't go quite as fast. There we go. So that is slightly less steep, right? This is steeper because it goes up or comes down faster. This takes longer to go up. And a flat slope would look like this to me. This is a perfect bunny hill. I'll draw a sad person because he's on his snowboard and the snowboard doesn't go anywhere. It just sits there. So we've got steep, slightly steep, completely flat. The question for us as mathematicians is, how should we distinguish steep from slightly steep from flat? Well, I would say here, I would say that there is no slope with this. So if I were going to measure this, I would say the slope, right, how steep it is, should be 0. And here I would say the slope should be a small number. And I would say here that the slope should be a big number. What do you guys think? Does that make sense? That the steeper it is, the bigger the number. And when it's completely flat, we say there's no slope, so it would be 0. Does that seem like a reasonable thing? I think it is, but I've been studying math for a long time, and this is exactly what we're going to be doing. Basically, if you've got a flat horizontal line, we're going to categorize that as a 0. And then as the mountain gets steeper, the number is going to increase and increase as it gets more and more steep. Now, we do have a question, though, because on each of these mountains, except for this one, because it's just flat, on each of these mountains, I've got one that goes up from the left to the upper right, one that goes, well, in my mind, it goes down. So like I'm kind of imagining you go up and then down, although I'm not sure how you snowboard up a mountain, but I'm sure someone has figured it out. Maybe we've got rockets. Ooh, that would be cool. Rocket snowboards. That wouldn't be dangerous. So we want to be able to differentiate between going up a mountain and going down a mountain. So another thing that we'd want to look at is if we were going to measure slopes on the side of a mountain, going up versus coming down, we want to be able to say one is one kind of number and one is another kind of number. And so what we do in math, normally if we were in person, we would all talk about it. But I mean, as much as I could sit here and go, what would you think? And then pretend I'm listening. Let me just make a suggestion. What if going up was considered a positive motion and coming down were a negative motion? Just for being able to if I say the slope is positive, you say, oh, okay, it's got to be one of those. Or if I say the slope is negative, it's like, oh, it's going to be one of those. So if I say it's a positive 1/2, then you would say, okay, it's going up and it's probably not very steep. And if I said it's positive a million, you'd be like, whoa, it's going up and it's really, really steep. If I said it's a negative one half, you'd say, okay, we're heading down and we're on one of these not very steep slopes. Or if I said it's negative a million, again, you'd say, okay, we're heading down and it's one of these really big, big mountains. So that's the basic idea behind the concept of slope, is that we're trying to qualify, because if you imagine each of the sides of the mountain, that's really part of a line. So we're trying to talk about different kinds of lines and to be able to really describe what they look like so that even if you can't see the graph, you know what's going on. Okay, so let's go and figure out how we're going to do this. Question: how could we quantify how steep the slopes are? And here's how mathematicians decided to do it. I know some people look at this and they're like, oh, wow, that's not what I would have come up with. And the answer is yes. The concept of slope has existed for at least a few hundred years. And so this is not likely to change. This is ideas people had a long time ago and possibly longer. The word slope is actually, we write M to represent the slope, and the M is described as the rise over the run. So we're looking at a fraction. We're looking at comparing the rise, how far up or down it goes, according to how far back and forth it goes. Now, let me go back to the first page and try to convince you that this actually makes some sense. Because I know most people look at that, they're like, oh, yeah, whatever. Mathematicians are always so weird. Not that we're not weird, but let's talk about it. What makes something steep? What makes something steep is that in the same amount of time, so if we let my fingers be that far apart, this mountain went from down there to way up there. In the same distance, this mountain didn't go very high. And in the same amount of distance, this one didn't go anywhere. So if we consider the same distance x and we look at how far the y changes, we can set up a ratio that will allow us to talk about how steep something is. Let me show you another example. If I imagine I'm going to go from here to here in the x direction. If I go straight across, y did not change at all. If I went straight across, so that slope is 0. In the same different distance, if I go from here to here, this is how much x changed. This is how much y changed. That's a lot more than 0. But then if I imagine, if I come way up here, that's even steeper because how much x change didn't change, but how much we change in the y direction, y goes from here to here, is quite a lot. So we're going to take a ratio of how much the y's change compared with how much the x's change. That's all. Now let's look at a couple other things. The rise is the change in y's, so that kind of rhymes. The run is the change in x, doesn't rhyme at all. And then we've got this really cool triangle guy, which is known as delta. That's a Greek letter, D. And basically, delta y means how much did y change, and delta x means how much x changes. And now here's the exciting part, is for the rest of your time in math, you need to know all of these things. So these all need to be memorized with each other. So if I say rise over run, you can fill in the other 4 things. If I say delta y over delta x, you can fill in the other 4 things. So the slope, which is represented by the letter M, which is the rise over the run, which is the change in y over the change in x, which is delta y over delta x. And in fact, on the very next page, there will even be a formula. So there's actually 1, 2, 3, 4, 5, 6 things that you're going to memorize in this chapter, in this section. And those need to go into long-term memory for as long as you're going to be in math, because from this moment on, slope is everything. In fact, But what you may or may not realize is that calculus is basically this. This is the little seed that will become calculus. It's going to take a couple years for you to practice a lot of math and learn some other math and get really good at some algebra. And then you'll be able to try calculus and you'll look back and you go, oh, that's right. This is absolutely calculus. This right here is one step away from calculus, believe it or not. So this is so important that we built an entire field on it. And so really worth memorization. So that's, I would definitely make sure you've got something, you've got a big star over here, you've got something that says, remember this. Okay, so let's go ahead and give it a try. I'm going to graph y equals 2x minus 1, and then using triangles, I'm going to calculate the slope. Okay, so let me move this a little bit. Y equals 2x minus 1. So I'm going to set up a table of values. If I plug in x equals 0, I've got 2 times 0 minus 1, which is 0 minus 1, which is negative 1. Okay. If x is 1, I've got 2 times 1 minus 1, which is 2 minus 1, which is positive 1. Okay. If x is 2, I've got 2 times 2 minus 1 is 4 minus 1, which is 3. Now let's see. X equals 0, x equals 1, x equals 1, x equals 3. 2 times 3 is minus, oops. I meant minus, not equals. 2 times 3 minus 1, following the formula. 6 minus 1, which is 5. And then I'm going to have to continue over here a little bit more. I want to also get x equals negative 1, make sure I know what that is. 2 times negative 1 minus 1 is negative 2 minus 1, which is negative 3. Okay, so I've got my table of values stuck in 2 pieces. I wrote a little too big to fit it all in there. And then let's see, I've got x's on both sides. I've got y that goes everywhere from 5 down to negative 3. I think that'll fit. Let me get, I'll go ahead and let's see, what colors do I want to use? I'll use black for my axes, believe it or not. So here I go, the y-axis. I'm going to put this a little bit low so I've got room to get all the way up to y equals 5. I've got x equals 1, 2, 3, negative 1. I've got y equals 1, 2, 3, 4, 5. There's 5. Negative 1, negative 2, negative 3, 1, 2, 3, 4. Okay, so I'm just graphing the line. Hopefully at this point, when you're watching this, you've done a whole bunch of graphing. So you're feeling more confident with your graphing. I'm going to go ahead and just plot some points. 0, negative 1, there's 1. 1, 1, there's another 1. 2, 3. 3, 5. Okay. And negative 1, negative 3 right there. So good news is they do all line up in a line. And I am noticing a pattern. I don't know if you guys are seeing this pattern that I'm seeing. And the pattern is, oh, I should have continued a little bit there. There we go. The pattern is every time x goes up by 1, y goes up by 2. X goes up by 1, y goes up by 2. X goes up by 1, y goes up by 2. That's an interesting pattern to notice. So let me start with A will be the blue ones. Okay, so x equals 0 right there. X equals 1 right there. So what does it mean to draw a triangle? This is what it means. You start at the leftmost point and you walk out along x, and then you walk up to get to y. Now, it's not all going to fit on the graph. So down here, I'm going to draw a copy of this. And let's talk about the points. So going across from here to here, that's 1 square. Going here to there, I count 2 squares. Okay. So the rise, the slope, which is the rise over the run, it went up 2 and across by 1. So that's 2 over 1, which is 2. Okay, let's try between 1 and 3. And let's make that one pink. So there's high contrast. So I'm going to start here at x equals 1, and I'm going to go all the way to x equals 3. That's this triangle. I walk to the right along here, and then I go up. Okay, for this triangle, this is a much larger triangle. And for this triangle, as I walk across, I go 1, 2. So that's 2. And then going up, 1, 2, 3, 4. That's 4. So my rise over my run, which is m, is 4 over 2. So that's equal to 2. Oh, look, got the same answer. Huh. So for the blue one, my slope is 2. For the pink one, my slope is 2. Okay, I need one more color. I'll use green for this one. X equals -1 and x equals 1. So let's see, there's -1 right there. Now I'm going to kind of have to walk along here, and I'm going to have to kind of step on this other one to get to 1. So this one's also a big one, and it kind of overlaps a little bit. So let's look at this. This is my green one. Okay. So as I move across, 1, 2, that's 2. And as I move up, I go 1, 2, 3, 4. It's up 4 squares. So my slope, which is my rise over my run, it went across 2, so that's down the bottom, and it went up 4. 4 over 2 equals 2. So the green one is also 2. So what's the point here? What do you notice about all 3 slopes? All 3 slopes are equal. And in fact, if we want to really check it, we could go from here, draw a little triangle, goes all the way up to here. And if I talk about the purple triangle, the really big one, let's look at how far this is. This distance is 1, 2, 3, 4. And then this distance, 1, 2, 3, 4, 5, 6, 7, 8. The slope, which is the rise over the run, the y's over the x. So even though the triangles get bigger, right? The purple triangle is way bigger than the pink triangle or the green or the blue. Even though the triangles get bigger, this ratio, because you're comparing the y, which gets bigger, and the x, holds on to this particular ratio, 2, 2, 2, 2, 2. They're all equal. So this is the thing. Any line, any given line, like this one, has a slope. And if you just happen to notice that there is a big fat 2 sitting right in front of x, and if you wondered, I wonder if that is a coincidence, it is totally not a coincidence. Turns out the number right in front of x, if you solve for y, is that slope. Ta-da! Okay, this is awesome. Let's see, I'm going to peek over there. Okay, I am not going to go any further with this video because we're almost at 20 minutes. And so I'm going to give everyone a break. Go get something delicious to drink or eat, and then come back and let's do the next video. It'll be, if you don't want to have to draw all these triangles, what are we going to do? It turns out there's a formula. So you don't have to draw any graphs if you don't want to. Woohoo! Woohoo! Awesome. Okay, so math on, guys, math on.